Hello, everybody, and welcome to your Earth Science Lecture number 22. This one is on air pressure, wind, and also on global wind belts. This is an updated lecture that includes a little bit of information on wind belts, so I'll get right into the lecture subject today. So, atmospheric pressure, and we want to take a look at your lecture assignment. So, I have it right here in front of me. So, first one is saying, how does air pressure change with altitude? So, your altitude, if you look right here, your altitude's on the vertical axis here, and as you go up, you'll notice what happens to air pressure. Well, air pressure, this red line is showing air pressure, so as it goes to the right, or it's increasing. As it goes to the left, it's decreasing. So sorry, I drew that backwards, but as it goes to the left, it's decreasing. Going to the right, it's increasing. So as you see, as you go up in altitude, it's decreasing as you go up. And in fact, it decreases very rapidly. By the time you get to 12,000 meters, remember about 3 meters per foot, 3 feet per meter. So that's, around 36,000 feet. That's about as high as like a commercial airliner would fly. You can see that you're at a significantly lower air pressure. You're only at about 200 millibars, compared to 1,000 at standard atmospheric pressure that's here at sea level. So here in Corpus Christi, your sea level pressure is going to be around 1,000 millibars. So those changes in pressure are mostly due to the fact that you have less and less and less atmosphere sitting on top of you. So when you're right down here, if you can see where I'm drawing, right down here at the bottom, at the surface, on Earth's surface, you have a lot of weight of the atmosphere sitting on top of you. But as you progressively move through the atmosphere, you have less and less and less of that weight sitting on top of you. So density goes down. This shows it very well, how density goes down as you move up through the atmosphere, and also air pressure goes down as you move up through the atmosphere. Now, one thing that I ask here on the lecture assignment is, how do we measure air pressure? Actually, more specifically, what units do we use? So the unit that I'm going to use most often in this class are bars, and that's usually what they use in the metric system. So probably you never heard of a bar before. It's actually a very useful unit of measurement, because with this unit of air pressure measurement, the standard atmospheric pressure that you get at sea level is equal to 1 bar. So that's really nice, because 1 bar just means standard, normal air pressure. So you are experiencing 1 bar of pressure more or less right now. Okay, whether you know it or not, you're under pressure all the time. You're actually under quite a bit of pressure. Another way that we measure pressure is pounds per square inch. You probably, if you've ever changed a tire or measured, this is supposed to be a tire that I'm drawing, but if you've ever measured the air pressure in your tire, you know that it's around, 30 something psi, right? That psi stands for pounds per square inch. You are actually under right now 15 pounds per square inch. So that's standard atmospheric pressure. That's yet another way of writing it. So 15 pounds per square inch is equal to 1 bar. Yet another way of writing it is inches of mercury. I know that's a strange way of thinking about it, but I could explain where that comes from. But for right now, just take it as a given that we use this kind of strange way of measuring atmospheric pressure called inches of mercury. And there's 29.92 inches of mercury at standard levels, at sea level. Okay. Of course, if we want to use the metric system, we don't want to use inches, so we can convert that to 760 millimeters of mercury. But I know there's a lot of different ways of measuring it, but it all means the same thing. 760 millimeters of mercury is 29.92 inches of mercury, which is the same as 1 bar, which is the same as 1,000 millibars, which is the same as 15 pounds per square inch. It's all just different ways of measuring air pressure, but it's all the same. So you probably experienced things like this, where maybe you had a empty bottle of water, or maybe sometimes you have a bag of chips, and you go into the mountains, you drive high up into the mountains, or maybe you're on an airplane, and you might have noticed that either your bottle of water shrinks or crunches together, or maybe it seems like it's about to explode. I know sometimes I take a bag of chips onto the airline or something, and when the airplane gets to the higher altitude pressure, low pressure, that bag looks like it's going to explode. And that's because of the pressure differences outside and inside, right? So In here, outside that bottle, there's high pressure. Inside the bottle, there's relatively low pressure. That's why it crunches up that way. So all these things are just kind of everyday experiences you might have had with air pressure. Yet another way that, by the way, that we measure air pressure is, I mentioned 15 pounds per square inch. Yet another way that I actually ask about on the lecture assignment is, what about in kilograms? Pounds per square inch is an English unit. What about a metric system unit? Yet another metric system unit. Well, 15 pounds per square inch is the same as 1 kilogram per square centimeter. Okay, so that's yet another way that you could write the same information. 1 kilogram per square centimeter. Okay, so sorry, there's so many different ways of writing the same idea, but they're all things that are relatively standard in when we talk about air pressure. So you have to be used to all of them. Now, when you see a weather map or something like that, remember, the only reason we're trying to understand all this stuff about air pressure and wind, et cetera, so that we can understand a weather report and understand what it means. And oftentimes when you see a weather report, it'll actually include a map that looks like this, showing high pressure and low pressure systems across the United States or wherever you're looking. Those high pressure and low pressure systems are depicted using these contour lines. So you can see this is a contour line right now that I'm drawing along in red. And what those contour lines mean is it's trying to show lines of equal pressure. So everywhere along this line marked 1020, which is, by the way, in millibars, is 1020 millibars. Okay, so it's a teeny bit over standard air pressure. It's just a little bit higher than standard air pressure. So it's about 2% higher, right? So what you see here, right? This would be 1028, so that'd be a higher pressure. 1024, that'd be even higher pressure. So if you're standing right here at point A and standing over here at point B, you would feel the same air pressure, okay? Because you're standing on the contour. In both cases, you're standing on top of the contour line. The contour line, again, is just a line of equal air pressure. So those lines of equal air pressure are called isobars. Iso means the same. Bar is, we're referring to the unit of bar of pressure. Okay, so these are called isobars. They're just lines of equal pressure, and it's how we depict pressure on a map. Now, a student one time asked me, does it always look like this? Like, is there always like a high pressure system over the Atlantic and always a low pressure system over here next to England and a low pressure system over here in Canada? And the answer is no. This changes day by day, right? So it's depends everything on the weather, and these pressure systems move around. So I want to ask you a question. If you were going to be the wind or be the air, and let's say you were over here at the high pressure area, where would you likely go? Well, because this is high pressure and over here is low pressure, many people might intuitively think that the air is just going to travel across the isobars and go to the low pressure area. And that indeed is what air would like to do. It would like to move eventually from the high pressure region to the low pressure region. Just like imagine if you were squeezing an empty bottle, an empty like milk jug or something like that. You're going to be squeezing the air out of it. It's going to go from a high pressure area to a low pressure area. So air always wants to go from high pressure to low pressure, right? But this is the thing. That's kind of surprising. It might actually shock you in a way. You might expect that the wind, right? Wind is just moving air. That the wind would just move from the high pressure to low pressure, right? Just like that. But that's actually not what it does. In fact, what you see right here, the red arrows right here that I'm circling, those are actually arrows showing wind direction. And if you look at it, they are actually blowing totally perpendicular, 90 degrees, to what I would expect. And if you notice, they're always blowing kind of to the right of what I would expect, okay? So I would expect, for example, air to go into this low pressure system, but instead the actual air is blowing to the right, always to the right of what I would expect. So you should be kind of looking at this and scratching your head, because it should be very strange. Why would it ever do that? And the answer to this, well, before I get into the answer, I actually want to explain this term. You'll notice in your lecture assignment talks about something called the PFG, or actually it should be the PGF, the pressure gradient force. So the pressure gradient force, let me get that. Hold on, I have to get an updated lecture assignment. Sorry, I just realized I have the wrong. I have a out of date one because I still have the PFG instead of PGF, pressure gradient force. So let me explain pressure gradient force. Pressure gradient force is the force that arises from differences in pressure. And pressure gradient force always moves from areas of high pressure to low pressure. So pressure gradient force is basically the direction that you would expect air to move in. If you were coming at this not knowing anything, you would just expect air to go from high pressure straight over here to low pressure, right? That's pressure gradient force. It's just the force that moves air from high pressure areas to low pressure areas. However, like I said, air doesn't actually move that way. In fact, if I were to draw in some wind direction indicators, let me get out a different colored pen. If I was going to get some, maybe I do green, and I'm actually going to show the wind direction, actual wind direction in green, okay? Actual wind direction is going to be like this. So it's going to be like this, always to the right and perpendicular to pressure gradient force. So you'll notice that it's very surprising. It's totally perpendicular, 90-degree angle to what you would expect wind direction is. Now, one thing, pressure gradient force, although wind doesn't go in the same direction as pressure gradient force is the force that is moving the wind, one of the forces. So when the gradient is high, that means that the isobars are spaced closely together. The gradient is high. That's going to make a stronger pressure gradient force, and that's going to result in higher wind. Okay, so over here you'll get higher wind. Now over here the pressure gradient force is lower because the isobars are spaced further apart. Do you see how there's more space between these isobars compared to these ones down here? So that's the difference. That results in a lower wind speed. Okay, so isobars are further apart. That's a lower wind speed. It's because it has a lower, weaker pressure gradient force. Okay. Now let's talk about why on Earth the wind does not follow pressure gradient force. Because knowing nothing, you would just assume, okay, what I'm drawing in green here, that's the pressure gradient force. You would just assume that pressure gradient force would be in the same direction as the wind, and that's not actually true. So what's actually causing it to deflect and move to the right of the pressure gradient force is something called Coriolis force. And Coriolis force is a fictive force. This means it's sort of, in a way, it's imaginary, but it does play a role in understanding why air doesn't move in the way why air moves in the way that it does, and why wind blows in the way that it does. So Coriolis force is a fictive force that arises from the rotation of the Earth. So you have to remember that Earth is rotating, right? And now here at the equator, it's moving the fastest. Here at the poles, it's moving it's actually not moving at all, right? Right at the North Pole, where the axis of rotation is. So in between, it's in between. Okay, so the fact that we're rotating changes the direction of air movement. Now, a good way to think about this is like a rotating record. So if you're over here at A, and you wanted to try, if you could kind of imagine this, imagine you were trying to walk on this rotating record. You were trying to walk towards B. You might try to go towards B, but you might find yourself veering off to the left. And the reason that you would veer off to the left, now of course if you're just walking this might not happen, but if you were maybe a ball rolling, it would. The reason that you veer off to the left is because you conserve the rotational momentum from point A, which you can notice that out on the outside of the record, notice how you're moving a lot faster than
than if you were on the near the rotational axis of the record. So you can see right here, this is actually a good way. You see how the pattern here, you can see the pattern more easily right here than right here, and that's because it's moving much more slowly right here near the rotational axis than it is right here. Okay, this is making me dizzy, so I'm going to stop. But anyway, that's actually what's happening with Coriolis effect. It's deflecting, because Earth is rotating, it's deflecting the direction of wind away from its intended path. So even though wind tries to go and tries to follow the pressure gradient force, it always gets deflected to the right or to the left. Now, in the northern hemisphere, the rotation is counterclockwise. So, we're spinning on our axis, are actually spinning counterclockwise like that. That's why the sun rises in the east and it sets in the west. And because we're rotating counterclockwise, we're always going to deflect to the right. We're always going to deflect to the right in the northern hemisphere. In the southern hemisphere, we're always going to deflect to the left. So if you look at this record, the record is rotating clockwise. So we're going to deflect to the left. If we were to try to move from the intended path, the actual path is going to be a deflection to the left because there's a clockwise rotation. In the opposite situation where you're rotating counterclockwise in the northern hemisphere, looking down on the northern hemisphere, that's why you get a rightward deflection. Okay, a really great way. Sorry, I got so many GIFs because it's the only way to really understand this. But another great way of understanding Coriolis effect is to look at this merry-go-round experiment. So look at these people trying, or these children trying to pass a ball straight across. They keep trying to pass the ball straight directly across, but it keeps getting deflected. And if you notice, it gets deflected to the left. It gets deflected to the left because they're rotating rotating clockwise, not counterclockwise. So do you see that? So this is really the best example that kind of like real life example you could have about why deflections occur the way they do because of Coriolis force. This is it in slow-mo. I just thought this is yet another demonstration, kind of looking down in slow-mo. So you can see a deflection to the right, and that's because this person, or these people, they're rotating counterclockwise. Okay. All right, so Coriolis force also works on other planets, by the way. You've probably seen depictions of like the famous red dot that's on Jupiter. It's actually a never-ending storm that is in part happening because of the strong Coriolis effect on Jupiter. Jupiter, by the way, it's a much larger planet than us. It's been 389 times larger than Earth. It rotates in only 11 hours. So it has a day in 11 hours. So it's got a really strong Coriolis force there. Okay, so just to let you know, Coriolis force is strongest near the poles, medium in the mid-latitudes, and weakest near the equators. Okay, so we're going to put weak, equator, okay, medium here at the mid-latitudes, and strong at the poles. Okay, so again, northern hemisphere, you get a rightward deflection. Southern hemisphere, you get a leftward deflection. Okay, now if you think about this, take another look at these maps with the isobars. So imagine this is the pressure gradient force heading into the low pressure system, right? So that's the pressure gradient force that I drew in green. However, the wind is going to go always to the right, okay? Deflect to the right, deflect to the right, deflect to the right, deflect to the right. And you'll notice what's going to happen is you're going to end up with a spiral. Okay, let me erase some of this. I got these annoying things coming out for some reason. That always happens, but notice you're going to create basically a spiral that's going to go inward counterclockwise around a low pressure system in the northern hemisphere. Okay, that's opposite in the southern hemisphere. Notice that, of course, outward you're going to have an outward pressure gradient force in a high pressure system, and that's going to again cause there's going to be deflection to the right because of Coriolis force. You'll notice that you get a outward spiral around a high pressure system. Let me draw that again so that you can see it. But you're going to get an outward spiral
that is clockwise because of Coriolis force. Okay, so clockwise outward spiral around high pressure systems, a counterclockwise inward spiral around low pressure systems in the northern hemisphere. In the southern hemisphere, the rotation direction is different because Coriolis force causes a leftward deflection instead of a rightward deflection. So in the southern hemisphere, you would get the opposite. You would get a low pressure system, would still be inward. That's not going to change. Still going to be inward spiral, but it would be going clockwise. A high pressure system in the southern hemisphere is still going to be an outward spiral. That's not going to change, but it's going to be a counterclockwise rotation. Okay, so I hope that answers all of the questions that you would have in your. Well, I have it right in front of me, so I can read what your lecture assignment says. I think that I've answered everything. Just to make it clear, Coriolis force works at right angles to the pressure gradient force. Okay, it works at right angles. So Coriolis force is always going to be right. It's actually shown right here. This is pressure gradient force, and that's Coriolis force. It's always operating at right angles to the pressure gradient force. Okay. So there you go. High pressure system. Pressure gradient force is like that, what I just drew. You always have a deflection to the right, and you end up with outward spirals going clockwise around a high pressure system, inward spirals going counterclockwise around a low pressure system in the northern hemisphere. Okay, so I hope all that makes sense to you. You can actually click this here, and this will show you, actually, I don't know if this link still works. Perhaps does not, but no, it's no longer. Oh, Adobe Flash no longer supported. I did want to show you this though. This is from the. Let me show you. How does it go? Global wind patterns. This is a really neat website. So this will actually show you global wind patterns at any given point in time. So I want to show you first the equator. And if you take a look at the equator, you'll notice that there are not very many swirlies around the equator. Okay, and you can also notice that wind, it's not moving too much, and it's also not swirling very much. If you want to start to see swirlies, you have to go to higher latitudes. So now I'm going to look down at the North Pole. And notice now, when I look down at the North Pole, I see a lot of swirlies. There's 1, 2, 3 over there, 4, 5, right? So I see a lot of swirlies. Now let's look at what the direction is up here. This is the North Pole, so looking at the northern hemisphere, and you can see a counterclockwise rotation right here. So is that a low pressure system or a high pressure system? Well, that would definitely be a low pressure system. Over here, what about this guy right here? Still a low pressure system because it's rotating counterclockwise. Let's see if I can find a high pressure system anywhere. You all see one right here? So it looks like maybe right here, that could be a high pressure system. That seems to be rotating clockwise. Okay, this is another low pressure system sitting off here off the coast of Spain. Okay, now if you go to the South Pole, you're going to see a lot of swirlies because a lot of them develop in the Southern Sea. There's a lot of wind in the Southern Sea. So now we see, what's that? It's going counterclockwise, or it's going clockwise, right? That's a low pressure system though, because we're looking at the Southern Hemisphere. That's going clockwise. It's still a low pressure system because it's the Southern Hemisphere. You can see maybe something vaguely right here that's counterclockwise. That would be a high pressure system in the Southern Hemisphere. Okay, so hopefully that's a little bit instructive to you. This is just a good slide, again, summarizing some of the things here. Oh, by the way, I didn't introduce this name yet. So we actually call low pressure systems. Another term we use for low pressure systems are cyclones. Another term we use for high pressure systems are anticyclones. Just FYI. Okay, so this summarizes everything I already talked about. Cyclones, low pressure system, pressure gradient force is inward. The spiral is going to be counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. For anticyclones, high pressure systems, you're going to have always a PGF, pressure gradient force, that's going outward spirals, and the spiral is going to be clockwise in the northern hemisphere, but counterclockwise in the southern. Okay? So I hope all that stuff makes sense. Now, you might ask, where the heck does all of this high pressure, low pressure stuff come from in the first place? So it actually arises from vertical movement of air. When air is moving up, it's going to cause a low pressure system. When air is descending, it's going to cause a high pressure system. So when air is blowing down onto an area, spiraling down, it's going to create high pressure. When air is spiraling upward, it's going to create a low pressure system. Okay, so it all arises from vertical movement of the air. That's where you get high pressure systems or low pressure systems. Okay. Now, I want you to think back about this. Think back to when we talked about adiabatic cooling. Okay, so when you have a low pressure system, the air is rising. As it rises, what's going to happen to the temperature? Well, I hope you remember that as air rises, it's going to cool adiabatically. It's going to cool down. It's going to reach the dew point, and you're going to end up with rainy weather. Okay, so whenever you get rising air, that's when you start to get clouds and moisture and rain and snow, thunderstorms, things like that. On the flip side, when you have converging air that's coming down and descending, that air is going to adiabatically heat up, so it's going to go from cool to hot. And it's also going to be at this point bone dry, because air that's at very high altitude has very little moisture in it. So as it descends, it's going to cool down, it's not going to pick up any moisture, and it's going to be bone dry, hot air. And what that happens, that creates kind of like sunny, clear days. So days where we have high pressure systems sitting on top of us, that's when you get really like sunny and warm weather. Okay. All right, so I think I answered everything of that section. I'm going to finish up with talk about Earth's global wind belts. So, that kind of gave you like a small scale, detailed look at how pressure systems work over the surface of the Earth. But I want to kind of zoom out and look at the Earth as a whole. So there are some very important, big, large-scale global wind belts that occur that you should know about. You probably heard in your life about the trade winds. There's another group of winds called the westerlies, and I want to explain kind of where these come from. They're very, very important, and I want to give you some sense of where these things come from. So, air at the equator, it's very hot. Okay, it gets a lot of solar radiation shining down on the equator right there. And that's going to cause air to rise along the equator. Okay. Now, when that air rises because of the high solar energy that prevails at the equator, it's going to start it's going to start rising, it's going to start cooling down, and it's going to start condensing once it hits the dew point. This creates a belt of clouds around the Earth, where the air is rising. So this area, you literally see it in this space photograph of Earth. There's literally a belt of clouds that surrounds the Earth. That belt of clouds is referred to as the ITCZ. ITCZ stands for the Intertropical Convergence Zone. This is where the air is coming together, it's rising, it's then cooling down adiabatically, reaching its dew point, and it starts spewing out all of its moisture. So this is where you get heavy rainfall, lots of precipitation. Okay, so the cool thing about the ITCZ is that you always get almost non-stop rain here. Okay, so the ITCZ actually does not stay put in one place. It likes to hang out around the equator, but it will move north in the summer and it will move south in the winter, and that's because it's following remember, it's caused by the excess of solar energy, right? So when the sun is shining brighter in the north during our summer, it's going to follow it. When the sun is shining brighter in the south, because it's their summer and our winter, it's going to follow that sun. Okay, So it migrates up and down, north and south with the seasons. That is what brings heavy rainfall to the equatorial areas. So if you look at where the rainforests of the world are located, you'll notice that a lot of the rainforests of the world are around the equator. Okay, so that's due to the ITCZ. Another thing that happens here, sailing ships that are trying to sail, of course I know we don't really sail too much now, for only maybe for fun, but in the old days when sailing was the primary way of getting around on the ocean, it was really hard to cross the ITCZ because there were no surface winds. All the air is moving up, okay? So we don't get any surface winds blowing across to blow the ship along. So what happens is that the ships had to just kind of sit and wait and drift through the ITCZ. They called this area of the ocean the doldrums. And the doldrums were a really horrible place because there was no sea breeze, there was no wind, it's very hot, it's very wet, it's very sticky, and you're just drifting, often for weeks. You're just drifting along. And it was a very terrible place. And still to this day, I don't know if you ever hear people say this, but maybe older people might say, oh, I'm in the doldrums, or he's in the doldrums, or she's in the doldrums. It means they're kind of in like a very depressed state, so that's where that word comes from, by the way. So like I said, the ITCZ migrates to the north during our summer. So in July, that's where the ITCZ is. And it migrates to the south during our winter. And you'll notice that when the ITCZ moves north or south, it's going to bring really intense rainfall to certain areas, especially right here in India. Actually, the rainiest place in the whole world is this village in northern India. This area, I shouldn't call it a village, but this city in northern India. And they experience what's called a monsoon season. So all the places that you see covered in red or covered in blue, those are areas that they're going to experience a monsoon season. They're going to experience a season of rain. And the rain is going to be dry for the rest of the year, and then there's going to be a period of intense rainfall that never stops. So India actually gets a very heavy monsoon season. Sometimes you can get a little bit of, even us, you can see that it's creeping up pretty close to us, right? We're not too far away. So we do get a little taste of this, because you'll notice that, generally speaking, our winters are drier. Our spring time is drier than our summer. Like during summer, August, it's September, we get kind of heavier rainfall. So that's how it is in Corpus. Now, just to give you some sense of how much rain you get during a monsoon, Corpus gets about 33 inches of rain per year. This place in northern India gets 428. So it's just bananas how much water this place receives. So monsoon seasons can bring tremendous rain to certain areas. Okay. Now you'll notice that what goes up has to come down. So at the end of this, what's called the Hadley cell. So the rising of the Hadley cell is here at the equator, but then it's going to come down at about, you'll notice, around the 30-degree mark. So between 20 and 30 degrees, this convective cell, the Hadley cell, it's a convective cell, you're going to notice that the air comes down at around 30 degrees. Now, if you imagine this, you start off at the equator, you start rising, you drop out all your moisture. At this point, the water is bone dry. Okay, it's also cold. And now it travels to the north or to the south, depending on which Hadley cell you're in, and it's going to come down around 30 degrees north, 20 degrees north, around there. And when it comes down, it's going to adiabatically heat up. So it's going to experience adiabatic heating. And what you're going to have are very hot, very dry air coming down at between 20 and 30 degrees north-south. So if you've ever used one of these hand bicycle pumps, you might have noticed that it can get, actually, if you are doing it really hard, you'll notice it'll get pretty hot. And it's the same reason, right? As you compress air, whenever you compress air, air is going to heat up. And that's actually what happens here. As air descends, it compresses, pressure increases, and it causes it to compress, causes it to heat up. Okay, so this brings a lot of hot, dry air to this area. So 20 to 30 degrees. If I draw in right here, you'll notice there's a lot of deserts between 20 and 30 degrees. Okay. So, the Atacama Desert, right? The deserts in Argentina and Chile, the Namib, the Kalahari in South Africa, the Simpson Desert in Australia, the Sahara Desert in North Africa, the Chihuahua and Sonora deserts in, even here in Texas, in the American Southwest, the Arabian Desert, right? All of these are what are called subtropical high deserts. So STH. STH stands for subtropical high. It is the subtropical high is the area of high pressure that prevails around 20 to 30 degrees north-south, that causes there to be high pressure descending air and creates hot, dry conditions. That's why, for example, when we talked about salinity levels in the ocean, I pointed out that surface salinities around the tropics are higher. Why are they higher? They're higher because of the STH. It's because of the subtropical high that comes down around 20 to 30 degrees north-south, creates a lot of hot, dry conditions. Okay, those are called the horse latitudes. And if you imagine this, there's all this air coming down right at around 30 degrees north-south. Okay, as it comes down, okay, it gets blowing downward. You can imagine that some of it's going to move to the north, some of it's going to move to the south once it blows down. Okay, so some of it's going to move to the north, some of it's going to move to the south, but it's going to get pushed to the right in the northern hemisphere. It's going to get pushed to the right or deflected to the right due to Coriolis force. So what you see is that there'll actually be a band of east to west blowing air going along this way. That band of east-west blowing air right here, that's called the trade winds. The band of air that prevails up here at around 45 degrees north, that's called the westerlies. It blows from west to east. Okay, the westerlies and the trade winds. So it's this Hadley cell and this big convective cell that prevails on the surface of the Earth, between the equator and the tropics, that creates the trade winds and the westerlies. And that ends up being very important for determining the track of hurricanes and things like that. There are other cells besides the Hadley cell. There's the Ferrel cell and the polar cells. These are kind of important because they control the jet streams. So the jet streams are actually created by the fact that there's rotation here, and it creates this sort of rolling barrel of air held aloft. That's what the jet stream is right there. So jet streams are also very important for controlling weather patterns over, America, among other places. It's very important for controlling the weather patterns here. Also very important, by the way, we'll learn later, for controlling hurricanes, what our hurricane season is going to look like. But anyway, that's all I have for you today. I think I answered everything in your lecture assignment packet. So I hope you have a good day. And please, as always, just let me know if you have any questions about this class or if I can help you in any way. And I will talk to you next time. Thank you.